Welcome to Review Recording 1D to accompany Instructional Recording 1D for Section 4.4 of Unit 4, Chapter 4, Mathematics 2200. We'll be doing some problem solving involving quadratic equations. Example 1. A ball is tossed from ground level into the air and its path is modeled by the function h of x equals negative 5x squared plus 100x minus 125. Where x is the horizontal distance in meters from a nearby building, and h of x is the height of the ball, above the ground we'll assume, in meters. Approximately how far to the nearest tenth of a meter does the ball travel horizontally? To help us understand the problem, I've made a quick sketch. The ball is being thrown from ground level, and well, we know it's at a height of 0 at some point here, and at a height of 0 here. The only thing we don't know is if the ball was actually thrown from the base of the building or some distance from it. Let's do a calculation. The height has to be 0 in order for the ball to leave the ground and for it to land on the ground. So we've got 0 equals negative 5x squared plus 100x minus 125. We can divide everything by negative 5 to get 0 equals x squared minus 20x plus 25. Since this will not factor, we apply our quadratic formula. X equals the negative of negative 20, negative of our b value, plus or minus the square root of negative 20 squared minus 4 times 1 times 25. All over 2 times 1. So we wind up here with 20 plus or minus the square root of 300 under the root sign, all over 2. Now using the plus case, I get 18.7. So that's 18.7 meters from the building there. And using the minus case, I get 1.3 approximately, which is how far the ball was from the building when it started. So the difference between those two different distances is 17.4 meters. In our next example, a rectangular pool measures 12 meters by 20 meters. A paved walkway of uniform width is to be built around it. The combined area of the pool and the walkway is double the area of the pool alone. Create a quadratic equation and use it to algebraically determine the width of the walkway to the nearest tenth of a meter. I start by sketching the pool. That's 12 meters by 20 meters. Its area is 12 times 20, which is 240 meters squared. We need that figure in a moment. Next, we're told that there will be a paved walkway of uniform width around it. So I'll represent that with an outer rectangle. There we go. The width of that walkway is uniform, so it's x meters wide all the way around. Now, the combined length of the pool and the walkway, all of this side right here, it's the 20 meters for the pool plus the two widths, 20 plus 2x for the length, the combined length. And likewise, vertically, the width, the combined width will be 12 meters plus the two x's. Should have an x down there. There we go. 12 plus 2x for the total there. Now, the combined area of the pool and the walkway is equal to the combined length of the pool and walkway times the combined width of the pool and walkway. Now we are told the area of the pool and walkway is 480 meters squared because it's double the area of the pool. The length of the pool and walkway is 20 plus 2x and the width is 12 plus 2x. So it looks like we've got a little bit of FOIL work here to do. So we have 480 is equal to 20 times 12 would be 240. 20 times 2x would be 40x 2x times 12 is 24x, and 2x times 2x is 4x squared. We'll finish this on the next slide. Therefore, we have 480 is equal to 240 plus 64x plus 4x squared. And getting it all to one side and reordering the terms, I have 0 equals 4x squared plus 64x, and 240 minus 480 will be minus 240. Everything divides nicely by 4 in this problem, and we have 0 equals x squared plus 16x minus 60. Now that will not factor very nicely. Using our good friend the quadratic formula, x equals negative of the b value, the negative of 16 plus or minus the square root of b squared, that's 16 squared, minus 4 times 1 times negative 60. There we go. I've slightly adjusted my root sign there, and I've got 2 times 1 in the denominator. So we'll have 16 squared, which is 256, plus, because of the double negative here, 240. So we wind up with x equals negative 16 plus or minus the square root of 496 all over 2. Breaking it up into the two cases, 1 plus, 1 minus in here, I get two answers, 3.1 meters, negative 19.1. That one is inadmissible, so our solution is x equals 3.1 meters. And we make a statement the width of the walkway is approximately 3.1 meters. In conclusion, many problems can be modeled by quadratic equations, but check for inadmissible solutions. And quadratic equations can be solved by graphing, factoring, completing the square, and quadratic formula. Try to use the most efficient method. In our two examples here, the most efficient method was the quadratic formula.